Perfect. Well, thank you for everyone who is tuning in today. My name is Leah, and for today's MTV Summer School Lecture, we are going to be discussing radionuclide monitoring and specifically radioxenon detection used for radionuclide monitoring. So let's get started. So this is our agenda for the lecture today. We are going to start with some history and background information that will lead us into our discussion about radioxenon detection. This includes history of Comprehensive Nuclear Test Ban Treaty and the International Monitoring System, the IMS right here. And we also are going to be talking about what radionuclide monitoring is, and then this background on radioxenon. We then are going to talk about radioxenon detection, and I have some examples of detection systems used to study this type of radioactive xenon. And then I'll also go over some current challenges that this type of research faces. And the main takeaways I want you all to get from this lecture is the ability to answer these questions, which are, what is radioxenon monitoring and why is it important? So like I mentioned before we get into some technical talk about radioxenon, let's talk a little bit about the history and the events that led to radioxenon monitoring being so important and the status that it is today. So the first nuclear explosion occurred on July 16th in 1945, and it was a test done by the United States during World War II. And since the beginning of nuclear technologies being in play, there have been efforts to expand this knowledge and use it for weapons, but there have also been efforts to stop the spread of these technologies, and which is called nuclear nonproliferation. So such efforts came into play with the first partial test ban treaty, the PTBT, in 1963. So this was a treaty that banned nuclear testing in outer space, the atmosphere, and in underwater. But a key component of this treaty was that it did not ban tests underground. So while this treaty reduced radioactive fallout, which was a big concern, testing continued and it actually grew. So we can look at this graph right here and we see that here we have the partial test ban treaty open for signature in 1963. And these were a bunch of atmospheric and underwater nuclear explosions. They mainly all moved down to underground explosions then, and they continued on for many years later. So after a few years later of that, another treaty called the Nuclear Nonproliferation Treaty in 1968 occurred. And this was an agreement more so that was signed by the major nuclear and non-nuclear powers at this time. And it basically led to cooperation and that these states would work together towards nonproliferation. And although this agreement did not actually prevent the spreading of nuclear weapons and technology, it was very important at the time with the Cold War arms race and these big concerns about nuclear war consequences that could happen. And it was a success in arms control advocacy and cooperation then between these nuclear and non-nuclear states. So then a few years after that, we have a group of scientific experts that were scientists from various countries around the world, and they started doing research into monitoring and data analysis for nuclear testing. So over the years, these scientists set up a lot of foundational work that would be known for the Comprehensive Nuclear Test Ban Treaty that would come about in the late 1990s. But prior to this treaty being made, there was this conference for disarmament in the 1994 to 1996. This was the period of negotiations for this through the UN. And the big things that were discussed at this time for these negotiations were a verification regime for country compliances, that there would not be any testing going on. There was also a debate about what the definition of a nuclear test actually was. And the writing for the treaty was very intensive, so that's why this part was so important. And there was also discussion of which countries needed to ratify the treaty for it to be in place. And lastly, if there were to be a timed plan for nuclear disarmament. And the first 3 points were compromised on and set for the treaty, but this last point was not. But as a result, we have what is called the Comprehensive Nuclear Test Ban Treaty, or as I'm going to refer to it, the CTBT, which was established in 1996. So what exactly is the CTBT? Well, it basically prohibits all nuclear explosions around the world, including testing. So from 1945 to 1996, there were actually over 2,000 nuclear explosions that had occurred. Here's a map of locations of known explosions, and I've highlighted here the first site of the nuclear explosion. Some of you might know it as the Trinity site. That was the one in 1945. And just some quick facts about the CTBT in like recent news. Since it's been opened for signatures, 10 tests have been conducted, and the most recent ones being done by North Korea. And also in February of this year, Cuba signed and ratified the CTBT, and Comoros also ratified it, making it the 170th state to do so. But so this treaty, in order for it to go into force, it needs all of these Annex II states to sign and ratify it. And Annex II states, there are 44 of them. These were the states that participated in negotiations of the CTBT at the Conference of Disarmament, and they possessed nuclear power or research reactors at the time of these negotiations. So North Korea, India, and Pakistan have not signed or ratified the treaty, and Egypt, Iran, Israel, and China and the US have signed it, but they have not ratified it yet. And the US and China are the only remaining nuclear power treaty, nuclear weapon states that have not ratified it yet. And this treaty established a couple of important things. It established a verification regime for country compliance and an on-site inspections regime where scientists actually go in and collect data from an area if there was suspicious nuclear activity or events taking place there. It also has an international data center, which holds all of the data from the different monitoring systems set up for the verification regime, and it can be processed and distributed to scientists all around the world. And the CTBTO was also created to promote this treaty and then run all of these previous things that I mentioned. But the big thing that I've been talking about and the big thing I've been mentioning is this verification regime. So let's talk about that now. So a major component of the CTBT verification includes what is called the International Monitoring System, or the IMS. And this is a system comprised of 337 facilities around the world to monitor nuclear explosions. And this includes 16 laboratories and 321 monitoring stations once it'll be completed. So here's a map of all of the different types of monitoring systems and laboratories set up around the world for the IMS. And I think about 90% of the facilities have been constructed and are in use. We're not exactly to the 337 yet, but we're getting very close. And the IMS also uses 4 areas of detection. So we have seismic detection, and this monitors shock waves, which the majority come from earthquakes, but if there are explosions done by humans, whether that be from a mine explosion, for example, or nuclear tests, the IMS would be able to detect these shock waves from it. Then we have hydroacoustic detection, and these stations listen for sound waves in water, in the oceans. And then we have infrasound stations, and these stations detect ultra low frequency sound waves that humans can't hear, but they are also emitted by large explosions. So with these 3 detection systems, these are important because they determine, if an explosion occurs, but the only one that can determine and verify if it was exactly a nuclear event is radionuclide detection. So let's talk about radionuclide detection. There are 80 total facilities around the world for radionuclide monitoring for this type of detection, and 40 of which detect noble gases as well, particularly xenon, which we are going to be talking about in a little bit. But radionuclide detection basically detects radiations and noble gases found in the atmosphere, and these are used to verify these nuclear events. So you can see on this plot, these are all of the locations of the radionuclide stations around the world. But what exactly is radionuclide monitoring? So basically it encompasses stations that detect radioactive particles like aerosols from atmospheric explosions, and it also detects noble gases, particularly radioactive xenon that is vented from underground or underwater nuclear explosions. And monitoring is done continuously. This is done 24/7. And these are just some examples of what these stations look like. So we have some people setting up or checking them out, but they can be unmanned and they just run continuously 24/7. They don't need people to be there to basically run shifts. But radionuclides aren't really new. They weren't just products made from nuclear explosions. They've been around for many years, even prior to the CTBT. And we have natural radionuclides, and then we have anthropogenic ones, meaning man-made ones, basically. So for the natural radionuclides, we have primordial ones, meaning that they have existed on Earth since its beginning, basically. So we have like thorium-232, uranium-235, and these radionuclides have very long half-lives. Thorium-232, for instance, its half-life is like 14 billion years. So those aren't going away through decay anytime soon. And then we have secondary radionuclides that come from the primordial ones. And we have some examples, including natural isotopes of polonium and radium. And then we also have ones that come from cosmic rays like carbon-14 and sodium-22. But radionuclide monitoring isn't really focused on those ones. They're more focused on the man-made ones. So we have, particularly for the CTBT, we have radionuclides relevant to them and then not relevant. So the not relevant radionuclides are ones that come from medical isotope facilities, for example, or nuclear power plants. And the ones that are relevant to the CTBT come from nuclear weapons. And I wrote non-relevant, meaning these ones just don't come from nuclear explosions, but they actually are a little bit relevant because the signatures from these types of facilities and power plants can actually interfere with the data analysis for these ones. But we'll talk about that in a sec because the signatures are very similar. So why exactly does the CTBT look for radioactive xenon or radioxenon? Well, radioxenon was chosen for three major reasons. And the first reason is that it is a noble gas, meaning it is inert and it doesn't really interact with material like soil or rocks that occur from underground explosions. And it's also has a very low solubility in water. And the xenon isotopes don't attach to dust or debris to make larger particles, and instead they remain in a gas form. So during the first hours after a test, these high temperature and pressure from the test can actually create fissures in the rocks, and then leading to an immediate vent where the radioactive gas can seep through and escape into the atmosphere to be collected by the different monitoring systems. So the gas can travel many, many miles with the traveling winds that go by, and then all the way to the detection site or the monitoring sites. So we established that noble gases are good for this type of monitoring. Okay, but why then xenon noble gas? Well, another reason that xenon gas was chosen was because it has the highest cumulative fission yield of all the noble gases produced from uranium and plutonium. And particularly, we look at the radioxenon isotopes of 131 and 133 metastable states, and then 133 and 135. And you can see the fission yields in this table right here. But if you look at, you might notice something with this graph off to the side, right, where you notice that for xenon 135, for example, the fission yield is about 0.25% coming directly from the uranium fission. But you'll also notice that fission products are also tellurium 135 and then iodine 135. And when these two isotopes decay, they can decay into xenon 135. So this is how we get that higher cumulative yield for fission over time, actually. So like right away after an event, we don't have much, but over time, we actually can get more xenon detected because of these decays. And then lastly, we look at radioxenon because the isotopes have long enough half-lives to collect data for verification, but not too long where it could interfere with some background. So actually we could expect to see isotopes of argon, krypton, and xenon noble gases after nuclear detonation, but we want to study the right one. So let's look at argon, for example. So we have like argon 37. We don't really see a lot of photons radiated from that. And the technology, I guess, to utilize argon 37 would be kind of very complex and very expensive for the CTBTO to continue this verification. Because as I mentioned before, these monitoring systems are basically running 24/7. So it would be very expensive to, I guess the technology would just be difficult to do. I believe there are some studies being done with radionuclide detection and this argon 37, but it's not the main subject for the CTBT. So then we also have krypton isotopes, but for krypton, these are too short-lived to get enough data, or they're like too long, like krypton 85, and that krypton 85's half-life is almost like 11 years. So we would get lots of high background in the atmosphere, and it could cover up emissions from explosions anyway. So because of the fact that xenon is a noble gas, it has the highest cumulative fission yield, and it has just like the right sweet spot for the half-lives, as you can see right here. This is why the CTBT looked to xenon for this particular radionuclide monitoring. So there's a couple things that happen when actually monitoring the radionuclide detection as well as with the radioxenon. And basically to detect each type of isotope, there are these plots created with a region of interest in ROI, and that's used to identify the emissions from the xenon. So here's an example of a plot right here where we have a beta gamma coincidence detection system where we have the gamma detector as a sodium iodide and then the beta particle detection from a plastic scintillator as well down here. And you can see if we plot the energies against each other, we get these different types of regions of interest that show prominence that this type of isotope existed. So if we look over on this side, for example, at this plot, let's take 135 xenon, for example. So the major gamma ray for a 135 xenon is about 250 keV. So if we look over here, that falls about right here, and then it extends all the way here to about 900 keV, and you'll see that this is our beta endpoint as well. So these plots are very useful for scientists with the CTBT to determine that these isotopes do have a presence, and then you can also see how many counts there are as well. And another thing, another type of technology that the CTBT uses for radioxenon detection are these types of isotopic activity ratio plots. So these are very important to distinguish between different types of signatures, whether they come from nuclear explosions, for example, or something like a nuclear power plant. So scientists were able to determine like this line of discrimination basically of what would the activity ratio be if something were a nuclear explosion, what would the activity ratios be for nuclear power plants. So you can see we have the ratios of 135 and 133 here, and then also the metastable states down here as well. Oops, sorry. So now I'm gonna switch gears a little bit now that we've talked about some of the background for radioxenon detection. I'm gonna talk a little bit about the IMS radioxenon detection systems. You heard me mention on the previous page that there was one that utilized a beta gamma coincidence system. That's one type of detection system, but there are also quite a few other ones. But the main goal of these detection systems is to investigate, again, these isotopic ratios and these background levels that we get in locations where there might be nuclear events and with the measurement systems. So again, we have certain types of facilities like medical isotope facilities or nuclear reactors that produce xenon as well. And because of this, we want, if the IMS collects data that there was xenon present in the atmosphere, we want to make sure that it was not from a nuclear reactor or a medical isotope facility. And in fact, that it was from a nuclear explosion, for example. It'd be really important because we don't want false positives or, we want to make sure that we're doing the best we can for that. And so the way that the IMS works is it has this automated gas process and this radioxenon measuring system where the gas is collected continuously again and filtered through this gas processing, and it is flagged and checked to see if there's a minimal detectable concentration, or MDC, of 1 microbecquerel per M3, 133, xenon. And the lower the MDC, these lead to fewer false negatives. So that's like a big thing that the IMS is using for detection systems, because the isotopes can then be better discriminated against from the background and all these different interferences. So that's something that's been going into play for trying to improve these types of systems. And because if we improve the sensitivity as well, from the lower MDC, we get more precise and accurate measurements, which will help enforce all of our different verifications regimes through the CTBT. But the radioxenon detectors in general, there's quite a few that I'm going to mention in the next few slides, but there have been some modifications to current systems to help improve how radioxenon is detected. And this includes decreasing number of photomultiplier tubes for easier gain matching, for example, helping with calibrations, improvements for better sensitivities and higher energy resolutions, as well as increased detection efficiencies. And big ones for helping with the detectors are increasing the sensitivity and the energy resolution, so that, again, they can help distinguish between those metastable isotopes from these ground isotopes that I've been mentioning. And the way that the detection systems work is there's some basic principles where there was this test done actually in 1999 with the International Noble Gas Experiment to determine the best way to make these detection systems. So there were a couple of different ways to do that, and the ones that were used for this experiment actually were first integrated with noble gas detection capabilities formally in 2010, after many years of studying to see which would be the best. And basically what happens is we have air that is atmospheric air that is pumped into charcoal-containing purification devices, and then that is isolated from, or the xenon is isolated from all of the extra contaminants. And all of the contaminants are then eliminated. So there could be contaminants like dust or water vapor or any other type of chemical element, I guess, are eliminated. So then we have resulting air that contains high concentrations of xenon, both in its stable and then unstable form. And then radioactivity is measured at these stations of the isolated and then concentrated xenon. And then all of that information is, again, sent to the International Data Center, where it can be analyzed further. So I'm going to mention a couple of the detection systems that are used. So there are gamma detectors. Here we have an example of the Spalex noble gas system. This was one of the types that was studied in those experiments prior to them being implemented formally in the CTBT. So this uses a HPGE type of detector with planar crystals and counting cells. And the good thing about these types of detectors is that it can detect all 4 of the isotopes with high resolution, and it's less complex than some of the other detection systems. However, a big con is that it has to be cooled. So that's not great when you have to keep constantly cooling these detection systems. And if it wasn't cooled, something bad could happen as well. And then we also have BEGE and carbon fiber counting cells. So this is a broad energy germanium detector, and these can cover 3 keV to 3 MeV of coverage, and it also has enhanced efficiencies below 1 MeV as well for energies. And then there's a different type of detection system called where we have 2 HPGE detectors and then planar crystals as well. And a good thing about this is that it uses a carbon fiber cell to improve detection sensitivity for metastable states. And it also has an increased full energy peak efficiency. But the con is that you have to increase your minimal detectable concentration from the spectra sum. Next, we have beta gamma detectors. So these detectors work at room temperature, so you don't have to use the cooling like you do for the HPGEs. And what happens is you have a electron detector, like a beta detector that acts as the sample container. And then you also have a photon detector, the gamma detector. So these were the types of detectors I was talking about previously with the beta gamma coincidence measurements. So a good thing about these is that you have background reduction because of the coincidence measurements that take place, where the gas is sampled through this little tube. And here you have the beta cell, or like the plastic cell that captures the beta particles, and then surrounded by a gamma detector for the beta gamma coincidence. And these have a near 4 pi geometry, which is good for efficiency measurements. And the common system used for the IMS uses this plastic cell, as I mentioned here, and then like a sodium iodide detector to collect the gamma rays. And actually, P&L actually constructed some new plastic scintillating gas cells, and they've been studying different combinations of those to help improve with the gamma detection systems. Another type of detector that is used to study radio xenon and help improve systems made at the IMS already are silicone detectors, for example. These ones are good because they have high energy resolution, low background, and they're sensitive to both photons and electrons, the betas. And they have good energy resolutions below 1 keV. And they also have different types where they have like a gas cell with 2 planar silicone detectors, surrounded by this well type of sodium iodide detector as well. And a big thing that is a problem with the IMS with this radio xenon is something called memory effect. So memory effect is when the xenon gas can actually diffuse into the scintillating material. And that causes a problem when you are doing these measurements, because then you'll have this additional background xenon present in the detector that shouldn't be there. So there's been a lot of push and talk about making new detection systems that don't have this memory effect. And for the silicon detector, for example, there is no memory effect when you vacuum the detectors for 10 hours. So that's pretty good for that. And these types of detectors can also be improved with HPGE and sodium iodides, and you get higher efficiency. And then also with this broadband germanium, and then something called a PIPS box, where it also minimized the memory effect as well. So I went through a couple of the detection systems, and the detectors I also mentioned are also just used to study radioactive xenon. For example, like in our lab, we are looking at beta gamma coincidence detectors to help improve systems already at the IMS. So there's just a bunch of different ways that scientists are looking to help improve how this xenon component can be detected in the IMS. But in general, gamma detectors have the best resolution for identifying these isotopes. But again, they require more cooling and therefore more field work. And then we also have these beta coincidence detectors with the plastic and sodium iodide, which are good because they can operate at room temperature, and that's good for being out in the field. But they've been shown to show worse resolution than the gammas, and it's harder to identify the different isotopes. And they also can, again, exhibit this memory effect. But big things that are into research right now for improving these detection systems is this increased need for sensitivity. So we can get these MDC levels below what they need to be and really hone in on capturing the xenon. And then also this memory effect reduction, because we want to just be able to detect xenon from the gases and not have any extra background coming in. And lastly, I'm going to talk about some challenges we have to radio xenon detection. So as I've been mentioning throughout this presentation, there are actually some similarities in emissions from these medical isotope facilities and these power plants. And discrimination between them is very important because, again, we don't want to have detection of what we think could be a nuclear explosion of xenon, but it could really just be from a medical isotope facility. So in this case, for instance, xenon can come from basically the production of when they're trying to make different isotopes for medical diagnosis procedures. And it also can come from the production of, I think, 131 iodine, which is used for gamma imaging systems, for example, and treatments and diagnosis for cancers as well. So, and I think xenon 133 is a radiopharmaceutical used for gamma imaging as well. So these isotopes are created in order to help people with the medical production, but they hinder on the CTBT, basically their agenda. So here we have this example again, where before I showed this, it was quite a little bit easier to distinguish between the nuclear power plants and then these nuclear explosions. But we have this gray area for this medical isotope production for these types of activity ratio plots. In particular, another challenge is the 131 metastable xenon measurement is difficult to do because of its concentrations are below the minimal detectable concentration. And then a big challenge is just the fact that we want to be able to determine if a nuclear test or nuclear explosion was actually there. So time is of the essence sometimes for these, and it's important that we urgently and effectively can test that the radio xenon in the atmosphere was actually from those as well. So we're always trying to look for improving our technologies in the IMS. And again, we look for ways to improve our energy resolution, to minimize this memory effect as well, and then also to increase our sensitivity for the detectors. So with that, we're ending a bit early, I guess. I was speeding through this. But in summary, we've talked about the history and background information. We know what the Comprehensive Nuclear Test Ban Treaty is now, which is the treaty to help prevent, it basically prevents the testing of nuclear weapons and is a big goal for nuclear nonproliferation. As part of the verification regime for that, we have the International Monitoring System that uses different types of detection, and the big one for us, for nuclear engineering, being the radionuclide monitoring. And then particularly the radionuclide monitoring that studies radioxenon detection because it's a noble gas and it has the highest cumulative fission yield and also has long enough half-lives but short enough half-lives that are available for the scientists to study at the different systems. I then discussed different radioxenon detection systems through gamma detectors, silicon, and beta gamma coincidence measurements as well. and then the challenges that we see through differentiating between the different isotopes and the background information coming from power plants, for example, or medical isotope production. And with that, there's actually a lot of information. I got a lot of this information from the CTBT website itself. So if anyone else is really interested in this type of research, I would really encourage you all to just look at the CTBT for radio xenon and just the history of it in general, because it had a lot of great resources as well. But if anyone else would like to know where I got a lot of this information, just feel free to email me down here, clarkleah@umich.edu, and I would be happy to distribute those resources to you as well. But with that, I would like to thank you all for coming, and I can take a couple questions if you need to. Otherwise, feel free to head out early, I guess. And then don't forget to come to tomorrow's lecture. That is our last lecture of the summer school, and I think it'll be a really good one. I'm also going to stop the recording right now as well.